Hello, my name is John Camier from Lawrence Livermore National Lab. It's my pleasure to present you today all-out kernel fusion and how to reach peak performance faster in high-order finite element simulations. But before talking about kernel fusion, let me introduce the context and the work behind high-order finite element simulations. First of all, what is the motivation and why are we interested in high-order finite element simulations? Well, finite elements are a good foundation for multiphysics simulations. Finite elements naturally connect all the different physics we need, and high-order finite elements work well on high-order meshes. It allows us to target large-scale parallel multiphysics simulation, and it triggers interesting needs for new research and developments. I am part of the MFEM team working on this modular library, and we are addressing flexible discretizations on unstructured grids, high-order methods, access to scalable solvers, and robust preconditioners. It is an open source software available at mfem.org, and it is the core of multiple next-generation application codes. MFEM is also part of a large ecosystem, Exascale Computing Project, FastMath, XSDK. Now, how can we reach peak performance in high-order finite element simulation with MFEM? MFEM is part of the SEED Efficient Discretization Co-Design Center of the Exascale Computing Project. SEED gathers 2 different national labs, 5 universities, and a large group of researchers. We are working on different applications such as inertial confinement fusion, compressible flow, climate modeling, medical research, combustion application, as well as additive manufacturing. One of the main challenges moving toward GPUs had been to rethink our algorithms in order to take full advantage of these new architectures. The partially assembled high-order finite element operators have been developed. Instead of assembling the full matrix A, each operator is decomposed as a product of other specific operators, parallelism, geometry, finite element bases, and underlying physics. It's optimal in memory, near optimal in flops compared to assembling the full matrix. Several SEED benchmarks have been released and played an important role. These are the mass and stiffness matrices benchmarks, BP1 and BP3, preconditioned Poisson solvers, BPS3, and performances are usually presented at throughput as shown in these results. Higher is better, but also importantly, the sooner you reach the peak, the better. We are interested to minimize the numbers of degrees of freedoms, or DOFs, required to reach this peak, which will help addressing strong scalability. Let me now introduce one possible way to reach peak performance faster with kernel fusion. One key idea is, of course, to try to fuse most of the kernels of such benchmarks. For example, if we try to do this for this conjugate gradient here on the left, where one line represents typically one kernel launch, we are going to need at least a few building blocks. We need a way to launch different kernels with different topologies, 1D kernels for vector operations, 2D, 3D threaded blocks kernels for the main partially assembled operators. And we also need specific WART levels instructions for the dot products, as well as a way to synchronize all these different algorithmic parts. And one natural way on NVIDIA's GPU is, of course, to use the cooperative groups abstractions or programming model. We will use the group partitioning for organization, and we will use the group collectives for synchronizations. So what can kernel fusion bring in terms of performances? On the left here is the best results for the SEED benchmark BP1 with MFEM after several years of optimizations. On the x-axis, you can find the numbers of degrees of freedom from 1,000 up to 10 million per GPU, and on the y-axis, the throughput measured in gigadofs per second for different orders. This is on one NVIDIA V100 and the last-in machine at LLNL. On the right, you can find the benefit of applying full kernel fusion on this benchmark. For low order, you do reach a better throughput, and for higher orders, peak performance is roughly the same, but we can discover the shift to the left that we were looking for, which means reaching peak performance faster with kernel fusion. In the middle, you have the two plots combined all together to be able to measure this difference. The shift can be measured by the number of DOFs required to reach 80% of peak performance. That's what we call the N sub 08. And for this particular mass matrix benchmark BP1, more than an order of magnitude of DOFs can be saved. This also means a reduction in time to solution by such a factor, or that we are now able to use the GPU efficiently even for smaller problems, which is something new. Now that we have seen the possibility of reaching peak performance faster on one benchmark, one important question is, can it be done in a sustainable way for other problems? This is a real paradigm shift where instead of reasoning as we have done so far with kernel launches, we are back to regular code directly executing on the GPU. One general way to address this challenge is to gain in abstraction using, for example, a more descriptive mathematical language. We want a sustainable way to generate these kernels, and we are going to augment the compiler internal representation to handle this abstraction. For finite element methods, the Phoenix project has formalized 10 years ago the Unified Form Language, UFL. It is a domain-specific language to declare finite element variational forms. On the left, you have the seed benchmark BP1 written in UFL. It specifies the mesh, the finite element involved, the function space, the boundary condition, the solution vector, the trial and test functions, as well as the linear and bilinear forms. We have added special function calls to help with the implementation. And starting with your favorite compiler frontend, you are able to build a modular toolchain that transforms UFL to C++ and raw CUDA. It is a source-to-source transformation which uses the graph of all the kernels that are going to be needed at runtime, the memory locations that are going to be read, written, or copied, allowing static analysis and optimizations. The first results so far were for the BP1 benchmark, a simple but important mass matrix solver. One main question is whether or not such gain in performance still holds for larger problems or solvers. One recent benchmark is the seed BPS3 bake-off problem, which is a full preconditioned Poisson solver. It is meant to test the scalability of high-order solvers on high-order meshes. Adding a preconditioner at the top-level conjugate gradient brings new elements. One first outer P multigrid with Chebyshev accelerated smoothing. A second inner low-order wavelet multigrid with again Chebyshev smoothing. And a third stage with the innermost conjugate gradient if required, depending on the options. There are, of course, multiple different partially assembled diffusion operators at each levels of the PCG for the outer P multigrid and its smoothing steps, for the inner wavelet multigrid and smoothing, as well as for the most inner CG. There are also multiple dot products of different length required for each iteration, which represents a total of nearly 100 of different kernels. The solver uses a high-order deformed Kershaw mesh, such as the one that we see on the right. I am now going to present all the different steps that led to full kernel fusion on this BPS3 solver. It is illustrated through NVIDIA Nsight system for a typical run with tens of thousands of degrees of freedom at order 6. Special care has been taken to make sure that the timing measurement is representative, and there are going to be 6 different steps that leads to full kernel fusion. On the left, we can see the setup phase with the right-hand side B, the finite element spaces FEM, the p-multigrid smoother setup with the power estimate of the maximal eigenvalues, and the wavelet smoother setup. The middle part shows one full benchmark of the preconditioned solver, which takes, without any fusion, 95 milliseconds. The pink part is for the outer p-multigrid. We can see the different levels of each reduction in the orders, using the transfer operators and the Chebyshev smoothing steps. The green part is for the inner wavelet multigrid, using 9 levels before hitting the inner CG, which means that we are not going down deep to the last singular level. And the blue part is for the innermost CG, usually doing a handful of iterations before going back up all the way through the wavelet interpolators and associated smoothing steps, the transposed transfer operators, and the second p-multigrid V-cycle. The first step was to fuse the innermost CG. We could have expected a better reduction in time, and it is exactly what had been done for the first BP1 benchmark, fusing a whole CG. In fact, it really depends on the weight of each kernel compared to its launch time overhead. This brings, however, the benchmark time down to 88 milliseconds. The next step is to fuse the inner wavelet multigrid, and most of the software toolchain offline work is, in fact, to be able to prepare these transformations by populating the context which holds the needs of all the different kernels. This brings the benchmark time down to 61 milliseconds. Intermediate step can be introduced in order to allow graph optimizations of the kernel launches and the data movements. The best impact is when we are able to reduce the number of copies, and these bring the benchmark time down to 54 milliseconds. One important step is the fusion of the outer p-multigrid. It brings a factor of 2 here, and the closest we are to having everything fused, the more gain we usually see. The benchmark time is now down to 26 milliseconds. The last part is the top PCG. We have now everything generated, embedded, and fused in a whole big kernel. I have summarized in this figure the different timings for each step. For this benchmark and these options, we are going from 95 down to 22 milliseconds, which represents a reduction by a factor of more than 4. One important thing that has been useful is the possibility to control the depth of the fusion. Having everything fused on one big kernel is good for performances, but limited in terms of debugging as well as profiling. Profiling can be addressed by generating specific code to time small regions, but it is not yet handled for more than that. And an NVTX API at the kernel level will be a huge improvement for profiling purposes. Now that we are comfortable with using larger problems, one last challenge to address multiple GPU runs is to bring the MPI communications inside the kernel. It is an important aspect needed for HPC simulations. Going back to the math, moving from a serial operator to the parallel version requires to wrap it in a P-transpose AP operator. For a typical constrained with the boundary conditions A operator, it is going to be a prefixed by one communication operator and postfixed by another communication operator. The prefix operator is going to prepare the buffers, send asynchronously the required data to the neighbors, work on some local vectors, and finally unpack received data to finalize the operation. The transpose operator is going to do the opposite after the application of the matrix-free A operator. This can be done through the NVIDIA's NVSHMEM library, which proposes a parallel API based on OpenSHMEM. It provides a global address space for the multiple GPUs, allowing fine-grained kernel-initiated communications operations. We are able to move from a standard GPU to CPU data transfers, then using the MPI interconnect, to a direct GPU to GPU link. I've provided here another session presenting NVSHMEM CUDA integrated communication for more information. Here are the latest fresh results obtained with a fully fused kernel with MPI communications for BP1 benchmark. We are still able to reduce the numbers of degrees of freedom to reach the 80% of peak performance by a factor of 5 for the higher orders. It is the first time we see such improvement while adding the MPI communication overhead. We tried 3 different implementations for the MultiGPU dot product, a reference one in blue based on the cooperative groups, using the atomic system call, which is straightforward, but limited because it can only be used on a single node. The standard second in orange is what MFEM typically uses. 2 stages, one at the thread block warp levels and the other for the MPI reduction on the CPU after some host transfer. And the third, all fused one in grid, using the NVSHMEM call to compute a global reduction directly. Even if we are not going to use a higher range of tens of millions of degrees of freedom per GPU, but more around the 1 million or less, it is comfortable to see that the path using NVSHMEM allows us to target the best performance. To conclude, I've presented you today a way to fuse kernel, which is a real paradigm shift. This shift needs to be confidently addressed with a sustainable software toolchain, starting from a higher mathematical abstraction, well suited for finite element methods. The MFEM library at Lawrence Livermore National Lab is the vector to target high-order finite element applications. This HPC library provides cutting-edge discretization algorithms in order to build powerful simulation codes. The Seed Co-Design Center, part of the ECP, has pushed to rethink our algorithm and try such new paradigm and optimizations. The main idea is, of course, to run efficiently on modern architectures, and being able to reach peak performance faster is mission critical for a large number of applications. We have shown that all-out kernel fusion can bring a significant reduction by an order of magnitude in degrees of freedom needed to reach peak performance, which also means a reduction in time to solution. We have been able to apply it on typical benchmarks, but also on larger solvers, and even with MPI communications for multi-GPU runs. Thank you for your attention, and I'll be pleased to answer any question.